In the previous lecture, we saw how when a mechanical wave coming on a string goes from one medium to the other medium being another string, so that there is a boundary, there is a reflection. In a similar manner, we are now going to see that when electromagnetic waves fall from on a surface from one medium to the other, there is going to be reflection. We are going to assume right in the beginning there is a reflected wave, there is an incident wave and there is a transmitted wave. Let us see one medium on one side has permittivity epsilon 1, on the other side it has permittivity epsilon 2. And let us take them to be non-magnetic, so that the permeability is the same, mu 0. When the wave comes from the left hand side, let us take its E field to be shown by this red arrow, and because E cross B should give me the direction of propagation, I am going to show you the B field by green color. It is going to be pointing this way. So, this is the B field and E field is shown by red. On the other hand, when it gets reflected, suppose I take E to be in the same direction as the incoming wave, then E cross B should give me the direction of propagation, and therefore, now the reflected B field is going to be the other way. So, this is B reflected. Let us call the first one B incident, this is E incident and E reflected. At the same time, in the transmitted wave, there is going to be E transmitted, and it is going in the same direction as the incident wave. I am going to have B incident, B transmitted, as shown here, in the same direction as B incident. So, we have set up what the electric field and magnetic fields are at the boundary, and now we need to apply the boundary conditions. The boundary conditions are E parallel is the same on both sides. This arises simply from Stokes' theorem as follows. If I look at this boundary and make a very small loop here, the E field on this side is like this, on this side is like this, then E dot d l is going to be equal to integration curl of E dot d a. Curl of E is nothing but d b dt with a minus sign dot d a, and this is E on the left hand side. Let me write left minus E r, because we are traversing the loop in two different directions. However, as we shrink the loop, we make this size, the red shaded region, almost of 0 width, the right hand side becomes 0, and therefore, E on the left should be equal to E on the right. So, E parallel is same on both sides, and this gives me the first equation, which is E I plus E r is equal to E transmitted. This is equation number 1. I will refer back to the earlier equation that we had derived in the string, which was y incident plus y reflected was equal to y transmitted. This is similar to that. In a similar manner, B parallel on both sides is equal. Why is that? That again follows from Stokes' theorem, because if I now take a loop like this parallel to B, then I have B dot d l across this loop is equal to curl of B dot d a, which is equal to mu 0 d displacement over d t dot d a. As the area is taken to 0, this guy goes to 0, and left hand side becomes 0, which again gives like the argument for electric field that B on two sides must be equal. So, this on this boundary I have E transmitted and E reflected, and I have B incident, B reflected and B transmitted. The two equations are E incident plus E reflected is equal to E transmitted, that is my equation 1, and the other equation is B incident, B reflected is in the other direction, B reflected is equal to B transmitted, that is equation 2. But now I know from my electromagnetic theory that B incident is nothing but E incident divided by V 1 in that medium, minus B reflected is nothing but E reflected over V 1 in that medium. This should be equal to E transmitted over V 2 in that medium. You may be a little uncomfortable because I did not do these equations for a wave in the medium, but the relationships are the same, and these can be obtained very easily by writing Maxwell's equation in a medium, which are, let me just write them on the side for completeness, which are divergence of D is equal to 0 in the absence of any charge, curl of E remains the same as minus dB dt, curl of B is equal to, again there is no free current. So, everything comes from displacement current is going to be mu 0 is the same dd by dt, and divergence of B is equal to 0. So, these again if you manipulate, they give the relationship that B is equal to E by V, and this immediately leads to V 2 E I minus E R is equal to V 1 E transmitted. That is my equation 2. I have gotten two equations, two unknowns, E transmitted and E reflected, and I can solve for them. Let us multiply equation 1 by V 1 and subtract equation 2. This gives me V 1 minus V 2 E incident plus V 1 plus V 2 E reflected is equal to 0, and this gives E reflected is equal to V 2 minus V 1 over V 2 plus V 1 E incident. Exactly similar relationship in terms of velocities in the two media as it was for the string, and similarly E transmitted will be given by nothing but E incident plus E reflected, which will give me 2 V 2 over V 2 plus V 1 E incident. So, we have got in this medium, which is epsilon 1 on one side, epsilon 2 on the other side, and therefore, there is some reflection and transmission, which are the incident wave does not get transmitted completely, and we have got E reflected equals V 2 minus V 1 over V 2 plus V 1 E incident, and E transmitted is equal to 2 V 2 over V 2 plus V 1 E incident. These two relationships are very similar to the relationships obtained for waves on a string. Notice that if V 2 is less than V 1, this implies E r has opposite sign to E incident. That means, it flips direction or there is a pi phase change. Let us translate these equations to equations in terms of the refractive index. Now, I know V is C by N, and therefore, E reflected is going to be N 1 minus N 2 over N 1 plus N 2 E incident, and E transmitted is going to be 2 N 1 over N 1 plus N 2 E incident. Again, you notice that if N 2 that is the medium 2, has larger refractive index than medium 1, the reflected wave has a phase change. This you have been taught in your 11th and 12th grade, but now we see that these arise basically from the boundary conditions on electric field and magnetic field. What about energy transmission? So, this wave is coming, gets transmitted, gets reflected. I should have the Poynting vector S coming in, incident, should be equal to the energy which is transmitted plus the energy which is reflected. So, S reflected plus S transmitted. Incident 1 is going to be V 1 times U, the energy density incident, 1/2. This should be equal to 1/2 V 1 U reflected plus 1/2 V 2 U transmitted, which is indeed what the energy flow is. This half cancels. This is going to be equal to V 1 times epsilon 1 E incident square, and the right hand side is going to be V 1 epsilon 1 times E reflected square plus V 2 epsilon 2 times E transmitted square. Let us see if this is true. Let us calculate the right hand side. Right hand side is V 1 epsilon 1 E reflected square plus V 2 epsilon 2 E transmitted square, which is equal to V 1 epsilon 1 times V 2 minus V 1 square over V 2 plus V 1 square plus epsilon 2 V 2 times 4 V 2 square over V 2 plus V 1 square times E I square. Now, I know that V is equal to 1 over square root of epsilon mu 0. Keep in mind that mu is the same, and therefore, V square epsilon is 1 over mu 0 for both the medium. And therefore, I can write this whole thing as V 1 epsilon 1, it is V 2 minus V 1 over V 2 plus V 1 whole square plus epsilon 2 V 2 4 V 2 square over V 2 plus V 1 whole square as 1 over mu 0, 1 over V 1, V 2 minus V 1 over V 2 plus V 1 whole square plus epsilon 2 V 2 square is 1 over mu 0, 4 V 2 over V 2 plus V 1 whole square. This is equal to 1 over mu 0, V 1, V 2 plus V 1 whole square, and inside I get V 2 minus V 1 whole square plus 4 V 1 V 2. This term is nothing but V 1 plus V 2 whole square, and this cancels with this term, and therefore, I get 1 over mu 0 V 1. So, this whole thing adds up to 1 over mu 0 V 1 E incident square, which is nothing but equal to V 1 epsilon 1 E incident square, as can be easily seen. So, you see that our amplitudes are such that they also satisfy energy conservation. So, what I have shown you in this lecture is through the boundary condition, when an incident electromagnetic wave comes, it gets both reflected as well as transmitted. The ratios of transmitted and reflected electric field have been calculated, and we have also shown through those that energy is indeed conserved.